Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for giving up Netflix or whatever it is that you were planning to do this evening. I didn't really want to make a presentation this evening and it's probably only about half done, but I think I can get across the main message. And I think it's so important because we're on such a tight time scale and I wanted to get this out there. I want you to understand where I'm coming from, and also that there is real science behind this, and this is real science done by people who are real scientists, and that you can probably put your feelers out there and get your thinking caps on and try and find other solutions. This is all to do with the opportunity to put proposals forward for dealing with first the tritium laced water that's at Fukushima, and so that's essentially kind of the focus of what we're doing. Now I have some really good news. I spoke to Alexander Parkhomov this week and asked him whether he would be willing to join the team as a lifelong nuclear expert, and particularly an expert in radiation monitoring and techniques. And he said he would be delighted. So we have Alexander Parkhomov with us, and that's fantastic news. Not so good news, we haven't heard from Matsumoto in a number of weeks, and so that is a cause for concern. But that being said, there are some other really interesting things to share with you tonight. And some of it came out of something that I actually only fully grasped live on the stream on Sunday. For those that saw it or have seen it since, you will know what I'm talking about. So I'm just going to check in and say hello to everyone we have here. So thank you, Jason, for your sacrifices for the greater good. Hi Corky, Slobodan, great to have you here. Slobodan, you can correct me where I go wrong. Hi Gordon, hi Infidel Apostate, and hi there, Blues Doctor, great to have you here. Okay, so let's get to it. So you might be wondering what you're looking at here, which is not what I want to show you. This is what I want to show you. What you are looking at here is a hypodermic needle, and at the end of that hypodermic needle, I'm going to change my mouse pointer here so I can give you something that you can see, or for those that are squinty-eyed, can't see very well like me. Give me just a second. It was all going so well. Give me a second. Nearly there. Okay, all right. I'll remember to do that next time. Honest. So what you're looking at here is a hypodermic syringe. Hopefully none of you have had to suffer that recently. Maybe you have. And actually, this is a YouTube video. You can go and have a look at it in your own time. The link is given here. But this is a chappie who has used a PET bottle and two pieces of polymer tubing and a whole series of normal kind of razor blades to create a HHO generator with a battery. And he's feeding the output into this needle here, and what you're seeing at the end here is the cut end of the needle. And I don't know if you're aware, but you might have seen it before. There's a very sharp cut off on the end here, and the actual capillary comes out of this area here, and the sort of knife edge of the needle is over here. And what's very interesting is in this particular image is, rather than a jet coming out, which it does have a jet in some of his videos, in some parts of this video, there's quite a stable plasmoid formed on the end here, and this might be to do with sort of capillary sort of what do they call them, capillary oscillation modes or something. We'll just have a look at a little paper on that. But this looks remarkably like the balls of fire, as the Japanese called it in their fusion journal in 2001. that we saw in the Vega experiments. And here is a Vega experiment, and this is a piece of nickel foil. And we can see this structure here. And this is from that January 2001 Journal of Plasma and Fusion Research by Sebastian Popescu and E. Lozninu. And this is their figure of the sort of double layer on the outside here in the center, and the plus in the center. Of course, there's negative going around the outside of that, but it's just representative. And I've lined these elements up here to match where it is. Now, the interesting thing that we established in the Vega experiments is that they like to be trapped sort of half in, like this one is here, and this is very common, half in and half out of the surface. Or if they're on something like a free thing like this, it doesn't matter whether it's, and we showed different examples of this, whether it's a flat piece of metal or a rod, you will see that it goes to the end. So it either attaches to the double layer on the end of the metal, but in this case the metal is actually going all the way through this ball of fire to the other side. And actually in some contrast levels, and in the video where I discuss this, you can see a bit of this metal poking through this inner layer into the double layer. But that's the kind of way these things like to arrange themselves. So just want to check if everyone can hear me. If someone can just say if the sound's all right, that would be great. Hi David, hi WP for Truth, hi Dan Moretti. Good, excellent, right. So so what I'm saying is that you're seeing a similar thing going on here, but it's very interesting because this is in a big plasma chamber and so forth, but this is in free air and it's still creating a plasmoid structure on there. So you know, this for me is quite an interesting observation in its own right. So I'm going to, thank you, I'm going to just flick back to my mugshot and I will go to the first of these things that I'm discussing here. So I got that image from the remote view blog Vega Disappearing Nickel, and there was something with the tungsten chop shop. So here you can see in this image where the metal is just sticking through, but it doesn't extend further than the outer part of the double layer, and that is essentially what we see when we look at this shot here. It's not really extending past the outer part of the double layer. And that's where that image is from, and these are on a more cylindrical section, various stable and unstable, and balls of fire that are wetting into each other with their kind of surface tension that they have. And this contrast just shows you a little bit of the extent of the double layer. And here is literally how fast it can form. It's like 1/30th of a second later, you've got a large plasmoid organized structure on the outside here. Okay, so let me get back to the presentation. So what we're going to be talking about today is this brief, supposedly a request for proposal by an organization called 9 Sigma. And I think the really interesting points that it's talking about here is essentially they've got these 1.25 million tons of tritium-laced water. So this is water that has been used to process fuel or to stabilize the reactors, and it has supposedly had its other elements that are dangerous removed from it, but there will be probably some other things in there. Now the challenge here is they're saying for the treated water, the concentration of tritium can be reduced to 1/1000th or less by separation treatment. And they're saying here that technology that can reduce the concentration of tritium to 1/100 or less at present is anticipated. So they think that you can get it to 1/100th, but they would like it, I guess, to 1/1000th. And so there would need to be, this is in their government project and verification tests, that they would like various things achieved, but I think that the minimum achieved amount of material that they would want treated in a day is 50 meters cubed. So quite a lot of water, as you can imagine. Okay, so I think this limit comes, if you do the calculation, they've been filling these tanks up for about the best part of 10 years, and they have 1.25 million tons, and I think it works out over 300 tons a day they've been adding on average. But if you go back in, like for instance the last year, there was like 1.2 or 1.1 million tons. So the rate of production of this problem water appears to be going down. So if you achieve the lower bound here, then you know, you would be able to maybe keep up with their production rate. If you were to get higher than the lower bound here and get closer to the higher bound, you might be able to eat into their stock of tritium water. Okay, so you can go and actually read this document if you go to the last blog post on remoteview.icu. This is all up there. Now, I have actually been working on the basis of 50 tons, and so the figures that I will talk about later are for 50 tons, but I think that whatever process is, it would have to be scalable necessarily, and that's what we would be looking to achieve. Okay. So Slobodan Stankovic found this historical document, and I can go to the patent for it, because the patent actually is from what is it? It's 1987, so it's expired. I mean, it was awarded, but it's expired. And so, well, I've got that somewhere. Let me find that. Oh, I got that there. Honestly, I have it somewhere. Okay, not that one. Yes, that one. Yes, that one. Okay. So here's the patent, 1602649, Federal Republic of Germany. Processing of tritium water. Now, the patent was issued all over the world, so there are versions in each country. I chose this particular version because it actually has the drawings in it here of how it works. So we'll just talk through that. And so this, I believe, is where they are coming from in their proposal, because they are talking about either where is it? They're talking about electrolysis or tritium can be reduced by separation treatment, and they talk about electrolysis as being one way, and by concentration by fractionation, and that's essentially what this patent is referring to. So here, it says concentration of tritium hydroxide. So that's TOH, and or ditritium oxide. So that's like super duper heavy water. Well, it would be if it had oxygen 18, but anyway, this is 2TO, like T2O. This is TOH, okay? So those are the two things that you would be looking to fix. It says, referring to the drawing, this drawing here, tritium water stored in container 1, this container here, is introduced into distilling column 2. So the water comes in here, you've probably got a stock that comes in here, and it goes into the distilling column, which is recycled into, from which water free from tritium, which comes out here, is recycled into the reprocessing. It's obtained at the head, so that's where our light water is coming from. So this would be the H2O. Okay, while water enriched with tritium is withdrawn from the sump. So down here we are taking water high in tritium down here, and then the water enriched with tritium is passed into an electrolytic enrichment cascade consisting of electrolysis cells. So you have the 3, and then you have 3, 1, 2, 3N. Okay, by the electrolysis, about 3 times hydrogen is formed than tritium. So when you do electrolysis of these tritium hydroxide and ditritium oxide, you get 3 times as much hydrogen coming out as you do tritium. So the concentration of tritium in the electrolyte increases from one electrolytic cell to the next. So as you go from on and on, you get higher and higher levels of tritium. Now, they say in reactors 4 and 4A, the hydrogen formed as electrolysis product is burned catalytically with the oxygen likewise obtained in the electrolysis, whereby water is obtained. So I guess they've got some platinum mesh or treated mesh in here, almost like your catalytic converter. And this HHO effectively, so you've got oxygen and hydrogen here coming out, goes through and gets reconverted into water. So one would imagine this would get hot. And then the hydrogen form is blah, 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 whereby water is obtained, which is recycled into the preceding cell. In the last cell of the cascade, tritium and tritium hydride in high concentration and oxygen are obtained. The tritium and tritium hydride are conducted to a storage site where the oxygen is recycled into the reprocessing. Okay, so the point that they're saying actually in the start of this pattern here is that actually when you have a high concentration of tritium in water, it's not actually that much of a problem, and that's what they're arguing. Because you just have to keep it cool and in a container, and it'll decay over a period of time. And that's true to a certain extent, but it's a problem when you've got 1.25 million tons of the stuff. And so that's what they're arguing here. In as far as tritium is obtained in the form of tritium water, which cannot be recycled, it must be stored. However, because of the radioactivity of tritium, the tritium water is decomposed into oxyhydrogen gas, a mixture of oxygen and hydrogen, and tritium steam, and therefore cannot be stored without careful controls. And in contrast, elementary tritium and or tritium hydride can be stored without controls, provided the heat generated is dissipated in a suitable manner. Okay, so there is the desire to separate this. And so I think that this is the reason we have this part of the requirement. They're really basing their requirement on trying to separate out and get basically mostly tritium, ditritium oxide to store so that you have less problem with it. Well, I think we can probably do better than that, and that is the basis of what I'm going to be discussing tonight. I may be wrong, but we must try. And so I want to talk about how I came to realise what I finally said on Sunday. And it really started in the earlier part of 2019 when I visited Selfmazes, and for whatever reason we were trying in our attempts very quickly to do some experiments with various metals that we could grab hold of that we had brought with us, or things that might be interesting. And one of those things was suggested by Dr. George Eagley, who was with me on that trip, and he suggested the 10 yen coin. Well, a 10 yen coin is actually 95% copper and 3 to 4% zinc and 1 to 2% tin. And you can imagine it being basically copper. This would be extremely conductive to heat. And the theory is, by some, that oxyhydrogen gas or Mars gas in this case is extremely hot. Now, when you look at when you look at Hoshi putting the gas on the coin, this is the side that he's putting it on, and he's moving it a little bit from side to side Obviously, he's got gas coming from torch in one hand, and he's holding the 10 yen coin in a pair of mole grips in the other. And so the registration is not going to be perfect. So there does seem to be a little bit of a softening edge, but we see this same softening kind of edge on the ball burn sample by that I have here from John Hutchison when we look at the feature in there that we've studied in quite depth. The interesting thing is when you look at this video, it sits there for a while, it glows, and then there's a moment where it just goes boom, it goes straight through the coin with a big flash. And when I was examining this coin, I found it quite striking because on the side that gets exposed, I've explained that, but on the other side, one half of it, almost like it was a induction effect, like a magnetohydrodynamic double spinning here. You've got a vortex going around here and a vortex going around here, but this one's pushing up and this one's pushing through. You have this cut line here, and the cut line is literally, it's razor sharp all the way down here, even through the embossed features of the coin. So you've got a leaf coming up here that's on the 10 yen coin, and it doesn't matter what it's going through, it's got a really, really sharp edge. And when I looked at this, I described it when I was looking at the microscopy images that year, I said it looks like a laser has cut through it. You know, it's extremely sharp, and it's not just that it's sharp. I mean, you can get some quite sharp cut lines when you're using, you know, it's acetylene and you're cutting steel and stuff, maybe. But it's the instantaneous nature at which you see on the camera this occurs. But it's not just this line. There's this bizarre straight line on the other side. Look at it here. I've zoomed into it here. And over here, you see this very, very sharp line that I've just shown you here. This very sharp line. And then over here, the sharp line continues. It's like, you know, maybe this is just the transition point between one phase and the next, but it is so hard and it's so round, it almost looks like it's been affected by something like this, where we saw that the balls of fire in the Vega experiments, they do nothing, and then once they get to the right energy, they start eating the nickel as if there was no resistance at all. And it does the same with tungsten as well. And so it appears to do it on the in part of that boundary, the inner boundary layer. So this alone would be interesting, but as we know over here, we've got all signs of exotic vacuum objects, which we've discussed, and also microplasmoids doing the snowballs on cobblestone. So we know that some residual effects of exotic vacuum objects are there. This is on the face that was impinged upon, but this is the blowout face, which has this very, very striking edge to it. Okay. So then what happened was I wanted to find out what a Marsa gas contained, and I was sent this analysis that was done on a prototype of the Marsa gas generator, gas produced by it very early on in the first few years of 2000 by a Japanese university. And what they found in there, amongst other things, obviously you've got H2, hydrogen, 60%, and you've got O2, 18%. So this is what it is. But you also have OH, H, and H2O, and H2O being the second largest fragment after the H2 and the O2. It's the third largest fragment. And then you've got N2 here, or CO, one of these two here. Anyway, my point being is, when I was looking at these, I was just seeing what could have caused some kind of laser type effect or something. And you know, I've heard of CO2 lasers, but there's very little of that. And you know, I know that microwaves can affect H2O, because that's kind of like what warms up stuff in your microwave oven. So I thought, well, maybe this is a maser. And so I looked up, you know, masers. And well, what I found was that the hydroxy group, OH, which by the way is the one most significant observation in the spectral lines of the of Slobodan Stankovic as he presented at ICCF 22. OH is like something that exists in the cosmos, and it self-mazes. It self-mazes. Now, it's not a lot. It's 0.8%, but it self-mazes. But also you can get mazing going on with the hydrogen, and you can get mazing going on with the H2. With the hydrogen in the highly energetic state, when the H2 is forming O2, does it do it instantaneously? I mean, the H2's got to be split and the O2's got to be split. So at some point, you're going to get a whole bunch of atomic hydrogen, and you're going to get O and H forming real time when you're actually burning this in this process. So, you know, we start off with some OH, we start off with some H2O, OH being something that can self-maze. Now, if we go and look at the Wikipedia for that, and I've given a link for that, but we'll go and have a look at that now. Okay. There's a couple of things I find very interesting about this Wikipedia article. So, and you can go and have a look at it in your own time, but it's they're talking about this self-mazing process of OH, and it says here, the high brightness. Now, this is something we see in a Mars gas. We see the bolometer. The bolometer only sees a few hundred degrees or below 1,000 degrees for both destroyed titanium and for tungsten. And we also saw in the video that I showed on Sunday, we saw that the indium, which melts at 156.6 degrees centigrade, something like that, that was glowing incredibly brightly. Well, look at it here. The brightness temperature of a maser is the temperature a black body would have if producing the same emission brightness at the wavelength of the maser. That is, if an object had a temperature of about 10 to the 9 Kelvin, it would produce as much as 1665 megahertz radiation as a strong interstellar OH maser. Now, I don't know if this is actually related. I'm just telling you the journey I went through. Of course, at 10 to the 9 Kelvin, the OH molecule would dissociate. KT is greater than the bond energy. So the brightness temperature is not indicative of the kinetic temperature of the maser gas, but is nevertheless useful in describing maser emission. Masers have incredible effective temperatures, many around 10 to the 9 Kelvin, but some of up to 10 to the 12 and even 10 to the 14 Kelvin. That's a lot of Kelvin. That's like a lot of Kelvin. So to be coherent, and I hadn't quite clocked it at this time, you've got some coherent emissions going on, and it's interesting, this 1.1665 megahertz. You know, so anyway, those are the things to think about. And the other thing that I found fascinating when I was reading this was polarization. An important aspect of maser study is polarization of the emission. Astronomical masers are often very highly polarized, sometimes 100%, in the case of some OH masers, in a circular fashion, and to a lesser degree in a linear fashion. This polarization is due to some combination of the Zeeman effect, magnetic beaming of the maser radiation, and anisotropic pumping, which favors certain magnetic state transitions. Now, where do I start here? I was able to observe nothing. I was able to observe nothing on the vibration plate from a maser, which is somewhere around here, over here. On the first evening after I had done the tests with a maser gas, I took one of the plates. It may have been this one. I don't think it was, but it may have been. And I put it under this Dynalite microscope, which I'd specifically bought. I don't know why, but I felt I wanted to look at things without too much reflection, because I knew I'd be looking at metal plates. So I chose one that has this polarizing ring on it. And you know what? Right on the camera, I couldn't see anything. But if I turned the polarizing, then suddenly a spiral strange radiation track coming out of a focal of energy, NG focus point, a cavitation spot. And so is it that this material that it produces actually can polarize the material that it's interacting with, so that it then can only be seen with certain types of polarization of light? I don't know, but that's interesting what I saw there. And then the other thing is that it's talking about magnetic beaming. Now, if you saw the extreme, the video, so let's see if I can find it. Extreme. Let's see if I can find it here. Extreme interactions. Let's have a look at it for not there. Remote view. Give me a sec. The extreme interactions one, if you remember, we saw these interactions between various emissions of in Dave's experiments, where you had these things coming out and they were folding around each other. Like a beam would come out one angle and something would come and bend round it, like instantaneous. But it was even doing it before the Evo got to the point of where the other one was crossing its trail. So this intense magnetic beaming that's coming out would explain the observations we're observing. So the whole thing comes together that it is coherent. And if it's coherent and it is matter, then it is coherent matter, right? Right? Okay, so that's kind of where I was, is that my explanation for why we were seeing this cut line and these kind of effects here. My explanation, right or wrong, it doesn't matter. That was my explanation at the time when I was going to ICCF, was that some kind of maser situation occurred, possibly with OH, or possibly with OH and real-time production of OH, and it just came into the mix and it amplified. And so that's the conclusion I had. And you know, OH was my first thing, and the possibility of OH forming as the burning process occurs. But then, just before Slobodan gave his presentation at ICCF 22, he showed me this image. And what you've got here is a carbon crucible. Okay, so this is a graphite crucible. And he actually made the hole through here by using the HHO gun, the torch head. And the interesting thing is that as that goes through, he finds that he gets this beam here, this very, very tight beam. Now you can imagine, as the gas is going in here and it's going into the tube, and you can actually see he's actually at a slight angle. He's actually at a slight angle. You can imagine that as it's going into the tube and it's hitting a slight angle, I was doing this today, I was watering the vegetables in the garden, and I had a watering can, and I got my hose and I'm squirting out of my hose my hydrodynamic fluid, and I'm hitting the edge of the watering can, and it's spinning around like this. It's spinning around, right? Now, if you just put it through the capillary that you've made, it would also have some drag on the side, and that would cause this to go around like that, and you would end up forming a torus. So, if you've got a torus type effect because of your fluid dynamics going through the capillary, and you're not straight on, you're going to have a spinning vortice type thing, then you've got a vortex, and so you've got a toroidal and a poloidal motion. You are effectively creating EVOs. And this enables some concentration, and it literally comes out like a laser, but it's not a laser. It's a maser in my view. Okay, so when he showed me this, it's like, well, I think I know what that is, because I'd already been through what I thought was what was causing that material to be cut, and also for the titanium and other materials. But I thought that I said to him, I think that's a maser. It's like a kind of like a microwave laser. It's not quite like that. If you go and read it, it's not actually like that, but they call it a maser anyway. And the interesting thing is if I can capture this, I'm going to try and capture this. So this was in September 2009. I'm going to show you his presentation, just a clip from it. Sorry if this makes you nervous, but I will do it anyway. So he gets a question, and I talked about this the other day. Here. He gets a question. Now, hopefully you can hear this. I'm going to move the mic down, so let's see if you can hear it.
I have many questions for you, but the main questions, what the type of the power supply used in your experiment? What? Microwave?
This is the standard electrolyzer, water electrolyzer using...
But plasma, what the generator is?
Oxy hydrogen gas only. No plasma, no energy input, nothing about the plasma generated by the gas itself. I start.
Okay. And the second very strange results in your optical spectrum, connected with your optical spectrum, because of no
lines.
Swan lines from graphite. Where is Swan lines?
From the graphite.
C2.
Yeah. Correct. I will just come back to the, for example, here.
Oxygen OHIC, but there are no...
So I don't know if you just caught that, but the main line that he sees is OH. Yeah, sorry, I know it's lower. I'm not got it looped through. But basically, Anatoly Klimov it notes that which is an observation that Slobodan Stankovic had, that the line that is most prominent is OH, okay? And it's a very, very strong line. Let me see if I can get this any louder here. I can maybe do it like this. Maybe I can, this should give you a little bit more headroom.
C2.
I didn't saw any C2 or C or on the other.
It's very strange.
It is. The only thing what it's even stranger than that is the broadband, what you see here. And as I discussed with someone, it may be even stranger that that we not see the carbon lines inside. This broadband signifies something really strange is happening here.
And the interaction between the graphite and OH jet will be in open atmosphere or not?
Open atmosphere, yeah.
Whereas CN, it's very strange.
It is very strange. The thing is that if you have only here, this one, this is OH radical, and that's for sure. And other lines are not present, so if there is a connection between oxyhydrogen plasma with azote, natrium from air, should be lines, but there isn't. This is picked up just at the output of the nozzle of the on the nozzle. So you can see only these gas coming out, and there is no interaction with the environment.
Okay, I sure we can discuss.
Okay.
My last question after your presentation. What is the type?
Okay, so essentially he he's asked what kind of microwaves are you using in your power supply to create the plasma? And he says, I'm not using any microwaves. Now, I mentioned why he said that, and I'm just going to reiterate it here. But the important thing is here is that Slobodan Stankovic is at the output of the nozzle, like quite close to where the gas comes out. He's only observing OH, okay? Only observing lines from OH. And you can see, if we go to that image from the presentation here, you can see here that the output of the nozzle is exactly where it's going into the carbon, the graphite crucible. And so that is where he observed OH lines only on the initial, on the analysis, the spectral analysis. So if it's compressed in there and you've got colloidal and toroidal motion going on, then you've got an opportunity for cohering that material, and that, I believe, is what is going on here. And so I believe that this presentation that Slobodan Stankovic presented in ICCF 22 in September 2009 forced the hand of Anatoly Klimov. And he shared this presentation on the 17th of June 2020, which I went into. And you can see these spiral structures here. And I'm going to go and just quickly run through those slides. But what he has in this chamber over here is a magnetron. He's got microwave excitation of gas to make it into a plasma. And then he uses a capacitor bank to do a discharge. And that causes a pressure pulse that forces the plasma through a polymer capillary tube. Okay? And going into the polymer capillary tube, you can imagine you would have drag causing some hydrodynamic shear forces leading to a poloidal motion, and if it doesn't come in exactly on square, it's going to end up with some toroidal motion as well. So you have everything you need to create EVOs. And so I believe that's what's going on. And in fact, Ken Shoulders said one of the best ways to intensify the power of an EVO is to put it through a capillary hole. And let's go and have a look at that, because I discussed that at when I went through that presentation, wherever that is. Okay. So this is the slides that I put together from his slides, and you know, he showed various phenomena. For instance, you've got a Mach 2 airflow coming out here, and it splits into three components: this one, that one, and this one. And this one is the one that we're interested in, and this doesn't appear to be affected by the Mach 2 airflow, other than when it's mixed with the other two. Okay, and this is interesting because, as I said, this was also done in the 1980s by Ken Shoulders. So he did an electrical discharge, and we're going to come on to why I'm mentioning a microwave and an electrical discharge a couple of times later in the presentation. It's very important. Don't let me forget why. But basically, he does a pulse discharge through a capillary tube and ends up with positive, neutral, and negative exotic vacuum object structures. So this was already shown by Ken Shoulders, and so it's all the same family of effects. And I believe that that is what you are seeing when you are seeing this. Okay. So that I believe Anatoly Klimov's hand was forced when he realized that actually Slobodan Stankovic had done something simpler. This is just oxyhydrogen gas going through a capillary tube, and it's creating the same thing. Whereas they had like a big fancy microwave system and a capacitor bank and a discharge and to do the effect. And this effectively is a pulsed event, whereas you know, if Slobodan can repeat what he did, it's not doing it all day long. But the important thing is here is that it was also created in the Vega experiments, these same spiraling tracks. Now, the difference here, in my view, is that you are building up coherent matter in a crack, and then it's destabilized, it breaks, and some of that matter is ejected out into these various beams. And if we go to the slides for that, get that. So we are here, and this is coming out of a crack between two bits of metal, and we get this beam here. There it is as a GIF anim. We've seen these things before. This is actually on Ken Shoulder's foil, and you can see an equivalent track to what could have been caused by a structure like this. Here's a very much larger one with the braided, twisted areas in it, and this is like the one that was produced on Baronoff's sample from a very, very different type of experiment. And this is the one that I've just showed earlier, and this was used by Jean-François Geneste to potentially explain what's going on with coherent matter waves. And this is the video where I'm referring to the magnetic beaming effect going on. So if I zoom into here, this one's coming up here, and it's bending over this one. It's coming over here, and this is affected here, and then it affects itself and comes back. But it actually is here. It's here when this one goes to bend round that one. So I was saying that there's something carrying out in front of it in a very intense way that's forcing this other structure to respond even before it gets to it. And so this is like a maser beam coming out of the front of the exotic vacuum object. And so what we have is a whole series of data points lining up from observations on Ohmasa gas and in Brown's gas historically, and HHO gases in general, to a hypothesis that OH might be important. The fact that it exists in the greater universe and it produces this maser radiation. The maser radiation produces intense polarization. That could explain the observations of only being able to see some of these structures under polarized light with optical microscopy. And it also produces this magnetic beaming. And so there's a whole smorgasbord of things that are lining up. And then you observe that Slobodan Stankovic is only observing OH lines. And so something must be going on, that when you analyze the gas through whatever analysis technique they're using, it doesn't represent the actual state of the gas when it's going through its business, when it's doing its interesting thing. And actually, if you take oxyhydrogen gas, and maybe Slobodan can talk to this, when you get at different distances between the sample, you get actually quite different interactions with it. And Slobodan can probably talk at much greater length about the different types of interactions. And if you study oxyhydrogen gas, it does have these different kind of structures in the flame. But I believe that this most interesting area where you can maze is in a certain zone, and I think that is very important for any solution where we are using it. Okay. So, I have to say that in the back of my head, when I was presenting on Sunday, it was at that point, live on that presentation that you saw, or you saw post-presentation, that it occurred to me that, if you have coherent microwave light, if that's what it is, can that influence the matter to become coherent? Because that's actually what you're seeing. You're seeing coherent matter. And then I got thinking about what Matsumoto had said in 2001, and I'll just see if I can dig out that. Where is it? Matsumoto had proposed creating itonic clusters, which we know he also refers to as microball lightning, by creating bunched protons with high energy from a LINAC and bunched electrons with high energy. Well, if you get bunched electrons, you get coherent electrons forming. And so this is effectively coherent matter in its own right. And he's saying by firing or introducing coherent matter to bunched protons, you end up by getting generation of microball lightning. Well, if you've got OH and protons and they're all bunched together, and you've got this poloidal and toroidal motion going on, then effectively it seems very reasonable that it's just another method to creating coherent matter. But that isn't really what was actually going through my head that split second real time on Sunday. What was going through my head was, damn it, this is a baser. It's a baser. And why I said it was because of this. I made this presentation, which you should go and see, on Steemit. And in response to that, I just sent the link to John after I'd written it, John Hutchison. And following the email of the above post, to John, he replied, "Hi Bob, a great article. I know Ken Shoulders was not listened to in our talks in Los Angeles, and also in the Canadian group. This is as it's written, the Boers. I didn't know, I didn't know what that meant in British Columbia. Maybe also Dr. Yao's Baser. This is the first time in my life that I came across the word Baser. Okay." I didn't know who Dr. Yao's was. I tried to search Dr. Yao and I didn't find anything. Dr. Baser's canon that slowly drifted off to the internet. Thanks for sharing this important information. Okay, first off, I'm just going to go and have a look at this presentation because you really should have a look at that. So here's the presentation, why, or the document. Why did a proven technology remediate nuclear waste get blocked? And this talks about the fact that they did 11 years of research on exotic vacuum objects. And this is after Fukushima. And this is David Yerth. And he said that he was basically forced to stop. He was working on Ken Shoulders. I think he was working with Hal Fox as well, who had bought the patents from Ken Shoulders. On high-density charge clusters, and he says you can shoot electrons out at the end of a spark generator, and those electrons, instead of dispersing away from each other like black bees in a windstorm, like you'd expect them to, they actually create little donuts, little torus of very specific diameter. When the torus is then guided by a magnetic field through a proton-rich environment, something like deuterium gas, deuteride gas, which is chock a block full of free protons, well, or deuterons actually, the little torus, because it's made of electrons highly negatively charged in the center, attracts the protons into the center of this little torus. It actually picks them up and carries them into the target. When they impact the target, because the protons have such high relative mass, at about 10% the speed of light, there's enough energy, kinetic energy, like a bullet or a bowling ball. There's enough energy when those things strike a nuclear target, the nuclei of a target material, that they disrupt it temporarily, not catastrophically, like high-speed neutron, not like a rifle bullet into an ice cube, but more like a ping-pong ball shot out of a marshmallow gun into jello. And what it does is it temporarily disrupts the nuclear structure. You get some neutrons coming off, you get some protons coming off, you get a lot of electrons freed up because of the orbitals are disrupted. You get gamma and they come back together. But when they come back together, the half-life is cut by 50%. 50%. Cesium-135, basically, feed it, so it says here, just by using the right kind of high-powered pulse electrical current in the right kind of environment, you can take that stuff, feed it through a tube, blast it with electricity, and absolutely eliminate radioactive emissions right down to the ambient background levels. You have inert material, okay? We did it for 11 years, and we had an invitation for the Department of Energy, and essentially it goes on to state that he basically got shut down. And then Dr. Yu came in 2010. They invited him in, and then he was shut down again under the Obama administration. Okay, so it was shut down again. So this is the thing that John Hutchison's referring to. But I think maybe he said Dr. Yu because of what I wrote here. That he maybe got a little bit confused in his email. Anyway, going back to the presentation. So Dr. Yao, so it's not quite the same thing, but I think he was trying to tell me something. And the thing about John is he sends stuff. I think this might sound a little bit odd, and sorry if it sounds a little bit odd, but I think he's got a weird kind of spiritual connection. It's a spiritual thing. He sends things because he feels that is the thing that he needs to send, and more often than not it is. But I wasn't very receptive when this first notification came through, and there really wasn't. I couldn't understand it because of this. But on Friday the 31st of May 2019 at 1936 he sent me this. It was just a screen grab, as he so often does, of only half of a piece of paper. But it says, research by Dr. Xu Yin Lo. I think this is the guy that he was trying to refer to me back in the previous November. A leading physicist in the field of particle physics, chief scientist at American Technologies Group, into the behavior of subatomic particles, has created a stable beam of massive particles. This beam functions the same way as a common laser. The important difference is that this being composed of massive particles rather than light. The beam is called a baser. Something accelerating this beam at extremely high energy levels are conceived to be the energy associated with such beam could theoretically exceed something thousand lasers by 1,000 times, by something 1,000 times. Okay, so that's kind of like what I'm seeing. So all right, so that's fine, but I still wasn't, receptive to this. This was 2 years ago, over 2 years ago. So and there was no attached information. It wasn't say, "Hi Bob, I think you should be looking at this." It was just the image. It was an email with this image, right? And then obviously I wasn't listening. And a year ago tomorrow, he sent the exact same image to me again. John Hutchison, Thursday, the 4th of June, 2020 at 1926. So almost a year apart, he sent exactly the same image, right? Now he's told me this week why that occurs. Or last week, he told me why that occurs. It's because his Facebook says, on this day last year, or on this day the year before, you posted this or something from 10 years ago or something. I don't know what it was. So he gets these reminders, but he just selected this image on this day and this day, nearly a year apart. So I thought, I had this in the back of my head after I finished the presentation. So I thought I would go and look up what baser was and just see if there's anything on the internet about basers. Right? I thought, is there anything on the internet to do with basers? Now, bearing in mind, I hadn't gone back to my emails to look to find the images I've just showed you. But it's crazy what you see. So, what I came up with on a very quick search, was this. Generating a coherent beam of bosons. A macroscopic baser, boson equivalent of a laser. Bosons such as deuterium particles generated by an ion source are injected into a vacuum tube, so as to excite motion on a circulatory path therein. Movement of the bosons in this path may be affected by the use of bending magnets 3 and 4, and focusing of the bosons into a circulating stream is assisted by quadrupole magnets 5 and 6. A coherent light beam from a laser. A coherent light beam from a laser is directed into the stream of bosons within the vacuum chamber to affect induced scattering of bosons within that stream, whereby to cause the stream to develop as a coherent beam of bosons, which is directed outwardly from the baser by suitable deflection of the circulating stream, such as de-energization of the bending magnets. In other embodiments, the bosons may be reflected in a linear fashion. Now, in the early parts of this the first paragraph here, he refers to something, and I still didn't recognize, because I hadn't looked back until yesterday, or the day, it was yesterday, to see what John had written to me about basers, okay? It said S.Y.Low, Physics Review, Letters, blah, 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 1984. So this paper is here. And essentially what he's saying is a mechanism for charge bunching. Charge bunching, that looks a lot like what Matsumoto was saying in 2001, but this is April 1984. Mechanism for charge bunching of bosons, okay, in high energy collisions. So essentially what he's saying is you can effectively create coherent matter by putting a laser into that matter, and there are some constraints and stuff, but he talks about it. But that is the paper, and it wasn't even then that I realized that this patent here was written by Shui-Lin-Low. Now, what was it? Who was the guy that John kept trying to tell me? Well, that was Dr. Shui-Lin-Low. Dr. Shui-Lin-Low. Okay? So, let's go and have a look at the patent a little bit closer and see what it says. So here it is in all its glory. I think this is the one. Yes, no, yes. Low Shui-Lin. So here is the highly complicated piece of apparatus. And that's the text I've just read you. And I'm just going to pick out a few highlights in here. I can find them. Maybe I'll bring up the page for you and I can see things quicker. It's not a short patent. Okay, so. Okay, I've got some things highlighted here. Have I missed anything? Okay. So the first one I've got highlighted here is: the availability of macroscopic basers has many practical consequences. By comparison with the laser, one immediately observes that the baser can be made up of charged bosons, which can be then accelerated to much higher energies, mega electron volts, giga electron volts, tera electron volts, etc., by normal mechanisms, i.e. low energy acceleration. This is exactly what David Yerth is talking about. Unlike photons, charged bosons are normally strongly interacting particles. Just as lasers help to study nonlinear effects, are rare effects in, and rare effects in atomic and molecular levels, basers may be used to create and to study nonlinear effects, exotic states, exotic scattering, and production processes in nuclear and hadronic levels. This is exactly, essentially, what Matsumoto was saying in that 2001 thing that I referred to earlier. And it's also exactly what the Lockheed Martin patent is saying you would be capable of producing coherent matter wave beams in their 2013 patent, which is even more complicated to achieve than this one. And both of them are vastly, and all three are vastly more complicated than using HHO gas. Okay, as we go on. Where a monochromatic deuteron, monochromatic, what does that mean? What does monochromatic mean? It means that it is at the same temperature, i.e. has the same de Broglie wavelength. Okay, so if you are getting things into a state where there's intense energy and they're all bunched together, as I've talked about before, you are forcing them into a monochromatic state. So if you've got monochromatic deuteron beam, where monochromatic deuteron beam is required, the quadrupole magnets may be turned off. Operation of the above described laser-induced deuteron baser, D baser, may be in either a continuous mode or maybe a pulsed mode. One use for the D baser lies in thermonuclear fusion. Okay. Thermonuclear fusion, in which the coherent deuteron beam is directed at a deuterium or a tritium pellet after acceleration to the required level by conventional methods. This is basically describing what David Yerth was describing, but achieving it in a different way. This method is similar to the implosion method using lasers, except that the substitution of a D baser renders the device many times more powerful. Many times more powerful. Like, so that's the National Ignition Facility. Forget it. This is many, many times more powerful in terms of the kinetic energy you can deliver. As an ion source for accelerators, the advantage of the baser is that in this case is that it's discrete momentum and simplification of the high energy accelerator because of the coherence of the beam. As an ion source for the microprobe or nuclei analogy of a microscope. Oh, you can make holographs from it. It also says you can coherent neutral particle beams may be obtained by placing a suitable material in front of the coherent charged boson beam, and it gives a couple of means of creating coherent neutral particles. But we already know from the work of Ken Shoulders from the 1980s and from the work of Anatoly Klimov from the 1980s, but reported, I believe, because of Slobodan Stankovic, that you can create neutral material out of this kind of approaches, but using capillary discharge. Okay. The invention can be applied to form a fusion reactor operating to release energy by the process. D plus D equals helium plus neutron. Well, in the case of Matsumoto, he's saying that doesn't yield a neutron. So if I go to here, so in this thing about acceleration methods of itonic clusters, I talk about Matsumoto also details all of the various reactions he has observed with itonic clusters, such as gamma-free fusion of deuterons to helium-4, stepwise transmutations involving addition of protons or electrons, many-body fusion reactions, mini-neutron star formation, electronuclear collapse, and electronuclear regeneration. These are the things that we can employ, and I've also put the reference here into the Lockheed Martin patent. Okay. One of the two deuterons may be provided as a compound of deuterium, such as deuterium oxide, D2O, such as in a pellet form, and the other may be provided by the baser of this invention. So what they are saying is, you can start off with your baser, and I'm saying that is our oxyhydrogen torch, or it can create coherent matter state. And then you can impinge that upon something else you want to fuse it with. Well, guess what? That was already done by Yul Brown in the 1970s, 80s, whenever it was. Okay? And it was already done by Takaaki Matsumoto in his electrolysis without realizing it. He's generating HHO. Okay? He's creating ball lightning, everything's going on. And he gets the same things that were observed by us when we exposed various materials to a Marsa gas. So a Marsa gas is doing it as well, and also the HHO, the oxyhydrogen of Slobodan Stankovic. So it's achieving the same thing. So what he's saying, to create a fusion device, and Matsumoto is saying it doesn't just do fusion, it does electronuclear collapse, electronuclear generation, and he observed it and he showed the evidence for that, and we've observed the same thing using oxyhydrogen gas. So we have many, many people observing the same thing, and these tests are so quick. To verify it is literally momentary. Okay, you saw how long it took to do those tests in a long continuous stream with unbroken, unedited. Okay, this takes a very little time. And so they've got a very complicated piece of equipment to create this coherent matter. So have Lockheed Martin, but HHO does it anyway. And you've pointed at your material, and you have the material that you want to transmute. Okay, and you have your beam coming out, and it interacts with it. So that is what they're saying. One of the two deuterons may be provided as the compound of deuterium, such as deuterium oxide, D2O, such as in the pellet form. Another may be provided by the baser of this invention. By this process, then, the deuterium oxide is subjected to one or more beams of coherent deuterons provided by one or more basers of the invention. The beams may thus be applied from various different directions, as in a three-dimensional array directed against pellets of deuteron containing material, these pellets being supplied sequentially, such as continuously to a reaction region. In comparison with nuclear fusion processes involving direction of coherent photon beams against a deuteron containing material in a well-known implosion method for producing nuclear fusion energy, the coherent deuteron beam from a baser of this invention has two distinct advantages. Firstly, each deuteron particle in the coherent deuteron beam has energies in the range of kiloelectron volts to 10 to the 2 kiloelectron volts, which is 10 to the 3 to 10 to the 5 times that of the photons produced in a laser. Second, the coherent deuteron beam itself interacts directly with the deuteron pellet, and hence can produce nuclear fusion more effectively and instantaneously. Hence, the size of such nuclear fusion reactor can be smaller, possibly allowing a device to be made portable. The nuclear fusion process of the invention may be practiced wherein coherent nuclei other than deuterium nuclei are fused. The process may employ mixtures of deuterium and tritium nuclei. Well, I don't know. How about having a tritium material colliding with another material you want to transmute? Okay? Anyway, so I found this very, very interesting. Now, let's just look in. I think there's a couple more things I wanted to highlight. A process for producing energy by fusing two nuclei, characterized in that at least one of said nuclei is provided in the coherent nuclei beam directed at the other of the nuclei. So this is basically what I'm going to describe in the latter part of this presentation. A nuclear fusion reactor effective to produce energy by the process of claim 60, comprising at least macroscopic baser effective to produce at least one beam of coherent nuclei, and means for positioning further nuclei for incident thereon of said beam. And nuclear fusion. So he just goes through a whole range of different nuclear fusion reactors. But essentially what I'm saying is, in 1992, two US politicians, Yul Brown demonstrated a BN2000 one. It's very similar to the one that we have in a location in the US, impinging upon a mixture of either cobalt 60, which has a 3-point-something or 5-point-something year half-life, and aluminium shavings and iron, or americium-241. One is predominantly a beta isotope, it's beta and gamma, and the other one is an alpha and probably gamma or whatever, but alpha decay mode. I think I'm right in saying that. The point is it's alpha and beta at least isotopes. Is it? Hold on, americium-241. Okay, well anyway, I might be wrong on the americium-241. But anyway, two different radioactive isotopes that come out of nuclear reactors and are considered waste. Although both of them are used. One is used for, irradiating vegetables and sterilizing things, and the other one is used and for silicon dioxide gem processing, and the other one is often used for smoke detectors. But that aside, he exposed it, and within a few seconds, basically, he describes, he's putting the gas on there, it builds, it starts to glow, it glows very, very brightly, and then there's a flash, and in that moment, basically all of the radioactive material is gone. Okay, there's a flash. And I believe what's happening is the coherent energy is building up and building up and building up until you get the yield of the material. And that's what you see in John Hutchison effect. It gets to a threshold and then it just gives. There's nothing that can stop it. Nothing. Not even the atom itself. It gives up the ghost. Okay, so that is, I'm saying that he observed that. A Marsa gas transmutes metal instantaneously. So, and whereas we don't have anything other than stories and stuff surrounding Yul Brown, we actually have the hard facts now. And the same for Slobodan Stankovic. He has some hard facts and they're shared. And the interesting thing is that both our data and the data of Slobodan Stankovic are the same kind of effects that were observed in lead and in momentary AC discharges in potassium hydroxide, producing carbon, in Matsumoto's work in 1997. And so the whole thing is consistent. Now, there are other technologies that could deal with the radioactive material. And you could argue the simplest way to do it is to electrolyze it and dump the tritium into the atmosphere because it floats and it goes up. That's not good either. It's less bad, in my opinion, than dumping it into the sea, where it goes straight into the food chain and it's there until it's decayed. But there's that. Now, the method that I showed earlier, that patent, which is, it would seem that is the basis for what that they are referring to in the RFP. That is, how should we put this? If you are very efficient and you wanted to convert 50 tons, let's say, of water to HHO, electrolyze it, like they're saying, regardless of the refining part of it, but if you wanted to convert 50 tons, that's going to take around about, if you were basically 100% efficient, a little bit less than 100% efficient, it's going to take you 8 megawatts, 8 megawatt hours. Per hour. It's a lot. I think that's right, but it's a lot of energy. Anyway, whatever it is, it's a lot of energy. It's doable, but it's a lot of energy. But remember, you've got to do that for each stage. You've got to do it for each stage. Now, if we had a means by which we could generate energy by, I don't know, for instance, creating really bright light and capturing that, okay, or we created nuclear level energy and we harness that to produce energy through a cycle, whatever means, and then that energy was used to feed the electrolysis process. But rather than doing many stages of first fractionating the water to get the heavier isotopes, and then electrolyzing and reforming and electrolyzing and reforming and cycling and cycling and cycling, rather than dealing with it that way and still having the tritium at the end, you haven't got rid of it, it's still there, it's just in a more concentrated form. You are capturing the atoms into the material. You're capturing the atoms into a different element, either by fusion or by nucleon exchange or by it triggering an electronuclear collapse, in which case you end up with mostly carbon. Right, so before I go into a more specific suggested solution or thing to work with, I just want to say something that I'm going to be doing with the, and this is now the right time. This is the right time to do it. This is the testing that I have long proposed for the supernova. This is the supernova. It is a microwave device. We have seen it do transmutation. It certainly looks like it did transmutation, and it produced these spheres with these north and south magnetic poles on them of crenellated iron oxide with what appear to be north and south structures on them, one with a carbon eye in it. So, and we've also seen on the inside of the structure these strike marks. Anyway, the point being is that I've proposed for a long time that the experiments that I wanted to do here is using some potassium hydroxide, potassium carbonate actually, and look for production of calcium. That has a 1.251 times 10 to the 9 years, and we would look for the calcium change in concentration via EDS. Okay, so that's one experiment. The second experiment we'd like to do is the 14 carbon plus neutrino goes to 14 nitrogen plus E. Now this might not be the neutrino, it might just be that the coherent matter destabilizes the matter and it goes in the direction that it wants to go, which is to release that electron that really doesn't want to be in there. This is what it naturally wants to do. It wants to go from 40 K to 40 calcium. 40 potassium to 40 calcium. It wants to naturally go from 14 carbon to 14 nitrogen. Okay, the half-life in this case is much shorter. This is like 1/3 the length of the universe, or 0.9 of the length of the universe half-life, and this is it 1/3 or 0.9? Yeah, maybe it's 1/3. Anyway, it's a long time. Anyway, it's 10 to the 9 years, regardless. And this is 5,730 plus or minus 40 years. This is much, much shorter than this. But if we can show using a mass beamline carbon dating, this is not radiocarbon dating, this is putting it into a mass beamline and looking at the numbers of 12, 13 and 14 in your starting material and your material after you've processed it in the supernova reactor. If we see that 14 carbon has dropped from our wood charcoal, showing that it's 5,000 or 10,000 years old, but it's not, they're both the same couple of years old charcoal, then we have caused the force beta decay of this 14 carbon. If we can do that for something that has 5,730 years, then perhaps, and by the way, this creates what looks like ball lightning in here, coherent matter. Everything looks like it's producing coherent matter in here. And in fact, many ball lightning approaches to creating ball lightning, use microwaves. Okay, and we've already discussed the microwave use in the Anatoly Klimov work earlier, and I also discussed it with another type of reactor that he showed. Anyway, tritium only has a half-life of 12.32 years. And so if we can deal with this, there's a really, really good chance we can stabilize this. Really, really good chance we can stabilize this. So these are the couple of tests I want to do. It's now the right time. I believe I've got a shield that I can work behind. This we can do at Allen's at some point, or maybe I can do it in the UK. This I will need to send to a northern European country, and it's quite pricey, but anyway, it's very accurate. So we will know 100% whether we've done that transmutation. Okay, so before I go on, okay, so is there anything is there anything I need to look at here? Okay, if you've got any specific questions, re-ask them, and I'm just going to get the biography of this chappie, which I have somewhere, because not only did he do that, by the way, this patent was rejected on the fusion claims, but later he made them in a different way and he got awarded. So it's not like this isn't potentially a real offering. And by the way, that is now also expired. So let me see if I can find. Here we go. So this is our chappy. Okay. It's, I think it must have been a younger virile self here. This is our chap, Dr. Shui-Yin Lo, American Technology Group, I guess. He had a PhD in physics from University of Chicago, 1966. Senior lecturer, University of Melbourne, Australia, circa 1985. Moved to Southern California, 1987. Joined American Technology Group in 1993. Visiting associate at Caltech, 1997. And here we go. Forming charges in a fluid and generation of charged beam. Forming charges in a liquid generation of charged clusters. These are very interesting details here. Method and apparatus for cooling electrons, ions and plasma. Particle accelerator. Electrically conductive solution comprising of charged boson ions. Method and apparatus for forming coherent clusters. Accelerator for coherent bosons. Method and apparatus for generating coherent bosons. And he's also got these publications, and I think this one, the people who are interested in water technology might be interested in this one here. It says 1998 proceedings of the first international symposium on physical, chemical and biological properties of stable water, i.e. clusters. There you go. Water clusters, crystals. Okay. Anyway, so there we go. That's the various things that you can see there. It's worth reading some of these patents. There's kind of like an extension, like I said, of the one that I'm referring to. But this essentially is arguing for me that what we've observed that he would like to have achieved with his patent, Brown's gas, HHO, oxyhydrogen gas, Matsumoto's production in situ, and the Amasa gas all do it anyway on a range of materials which I have demonstrated and pointed to. Okay, so what do you got? Have you been looking at my notes, Bob? Oh, I don't know where your notes are. You'll have to point me to that. No neutrinos that there in the universe is purely electric. Well, maybe, Matty, but you know, I can't see them, so I can't really argue. But I look at observable outcomes. So if I start with tungsten and I'm putting Amasa gas on it, and these elements come out, then something happened. These things cluster together, so you can see them doing that in the Vega experiments, and we know from the Vega Valley that they can get rather large, many hydrogen molecules across. What if you could control the process at room temperature? Well, there's every reason why you should be able to do that. That is what, to a certain degree, John Hutchison was doing. Bob, did you hear about Tesla's ray of death? Yes, in 1930 something, he had a open-ended dry steam vacuum tube. So he had dry steam coming down a tube that created a vacuum, so it was basically like a vacuum tube and open-ended, and he had tungsten wire fed in or mercury, and he did his pulses. That produced microscopic electrical particles of matter, I think he described it as, that went through the water steam and was able to do stuff. Okay, so I'm not going to debate particles today. Can bases interfere? I'm sure they can. I mean, scalar bases. Okay, so I'm going to make a suggestion now. And now this part of the presentation I haven't got organised very well. So I'll just have to wing it. What have I got? What have I got? Well, firstly, I wanted to speak to maybe the first slide and what may or may not be going on there. So essentially, what's going on to create this, where you've got the gas coming out of here, but you've got the sharp part of the needle here with the end, and it appears to be creating the ball of fire around there. How is that happening? Well, you can imagine the shear forces, the toroidal forces, they're coming out here, and maybe they're creating a kind of a vortex around here and a vortex around here, which is a kind of capillary fluctuation. And if I close that, you can see this is actually a water droplet with pulses going into it, and there are various modes. So here's a capillary tube. So the water droplet, of course, is a piece of fluid, and this is a fluid dynamic process. And these are the modes that you can have going on, and this is their experiment. And here are some potential eigen modes, and so you can end up with these kind of nice structures forming in there. And so I'll share the links to this paper so that there's a close up on it. So one wonders where the water is that's being produced, unless it's just being emitted as steam or it's being cohered or what's going on. But there's not a lot of gas coming out of here. But I found that fascinating that he was able to create that on the end of that tube, and it's worth attempting to replicate that. And so maybe Slobodan can do that. Okay. So, as we have seen, for instance, in the tungsten and in many other experiments, calcium is produced very readily by LENR systems. And why is that? Well, in the case of the 225-day reactor by Alexander Parkhomov, I was told just before I gave my presentation at ICCF 22, I said, why are we seeing all this calcium in here? Could it be this pathway? What is the inside core of your reactor? And he disclosed to me, so that I could share it, that it was silicon carbide. And silicon carbide, if you take silicon and carbon, that is, silicon is, say, 28, and carbon is 12, you put those together, you get calcium, don't you? So, you there you go. So, you can create the isotopes of calcium from the isotopes of silicon and carbon. And so it was unsurprising. In the case of the Amarza gas versus indium and the Amarza gas versus tungsten, you are getting probably electronuclear collapse and regeneration of elements. And so it's coming from the very heavy elements going down to the lighter and then also fusing. So you've got fission fusion going on, whereas with the silicon carbide in the 225-day reactor, you've just got straight fusion going on. But calcium is one of those kind of hard stops. It's a very high proportion of the Earth's crust, which in my view is telling you, with 4.5 billion years of experimentation of high intensity electrical and sparks and hydrodynamics and cavitation going on, that the nature wants to create a lot of calcium. And so it's a good thing where if you wanted to impinge upon it. And the other thing with calcium is that I think it was in 1926, you can go and have a look at this, 1924 maybe, 1826, 1824, sometimes in the early 1800s, it was found that if you heat it up in the form of calcium carbonate, which is basically chalk, very, very cheap stuff, and you heat that up, the carbon dioxide is driven off and you get calcium oxide, and calcium oxide then glows extremely brightly. And calcium oxide is called lime, and lime glowing in this way is called lime light. And lime light, it was first used in, I think, in a evening puppet show or something in 1820 something. I think that was, I might get these dates wrong, but you can go and have a look at it. We could use a very, very cheap material, electrolyze the tritium laced water, and impinge upon that very, very cheap material. The carbon dioxide would be driven off. You could pre-drive the carbon dioxide off, and then you would burn jets onto that with a view to transmutation. Now, I will show you what this looks like with a YouTube video, but I won't play it all through because I don't want to get a copyright strike. So just let me find a suitable place, and hopefully with no adverts going on. Let's just get there first. Okay, that'll do. I'll leave it on the opening frame. That'll do. So, in theory, no, it's not the opening frame. Let me go to a place. Okay, so this is a piece of lime. This is a oxyhydrogen gas, and it's going on here, and it's producing an extremely bright light. Now, what I've asked Slobodan to do is to try and do this experiment. Have you done it, Slobodan? Have you done that experiment yet? Well, I've asked him to get the spectrum of this because I wanted to know, how much is UV and how much is bright light in terms of normal visible spectrum of light. So anyway, this can produce a lot of light. Yes, exactly. And put yourself into the limelight. I'm going to now find. So the interesting thing is, when this is over and the calcium oxide is there, it will then just reabsorb carbon dioxide and become calcium carbonate again. So it puts a bit of carbon dioxide into the atmosphere when you start, but it gains it all back. So this is carbon neutral, as it were, as a process. So I'm now going to look for what am I going to look for? I am going to look for some reactions. Let's have a look at some reactions. Now, the beauty, if you didn't know this, of the MFMP's Lena reaction calculator is, firstly, thank you again to Philip Power, and thank you for working with me on the programming and doing such an amazing job. And thank you, obviously, to Alexander Parkhomov for doing the first calculations of the data. But the calculator is rudely good. It's rudely good at predicting. So if you go and look at historical low energy nuclear reactions papers, and you can do that by going to nanosoft.co.nz, as you see up here, nanosoft.co.nz, and you click on select Lena events, and you go here, and you can type in a name, or you can type in a year or something, and you can find out Lena papers. So if I go to Matsumoto and I go refresh pre-filtering, we can see a load of papers here from Matsumoto, and if we choose one, we might be able to see a link down here to go and see it. Okay, so you can go and have a look at that in your own time. But if you go and look at the data of the elements synthesized from the input element, then what you find is that this reaction calculator is very good at predicting the observed outcomes. Okay, I'm going to scale that up a bit so maybe you can see it. Okay, now you can see a whole bunch of reactions that I was working on earlier today to do this. So let's go and have a look at these. So well, let's look at fusion, where we have protium, deuterium, tritium, calcium, and carbon. And then we've got calcium. Well, we don't really need the carbon in there. Let's lose the carbon. So that one. Let's have a look at the output from that. So you can see here that you can get helium produced from protium and tritium, helium-4. This is fusion. Deuterons and deuterons go to helium-4, so we get a bunch of helium. So that can deal with some of that. And if you take tritium, the first one that is tritium and a calcium isotope, and there's not a lot of calcium-42 actually. But anyway, you get scandium-45, and that's a very rare element actually. In fact, it's called scandium because I think it was found in Scandinavia, but it's actually a really rare isotope, element rather. And you can take tritium down here and oxygen-16 and get fluorine-19. Okay, so there you go. You've got a bunch of reactions, and some of them are quite high energy yielding. So the tritium and calcium there is 17 MeV, and so forth. So there's one to have a look at. That's fusion. And let's look at 2 to 2. 2 to 2. 2 to 2. Okay. So in this one, carbon-13 is rare, oxygen-18 is rare. If we go down to the calcium-40 is the most abundant by far of all calcium, but calcium that is rare, so we don't want to worry about that. So let's go to the first calcium-40 that we see. Okay, so calcium-40 here with calcium-40 there with tritium. If you look at that line there, produces helium-4 and potassium-39. Now, why is this interesting? Well, potassium-39 is the most abundant isotope of potassium. So, in my view, since potassium is quite abundant in the crust, but potassium-39 is the most abundant potassium, we could produce, there's a good likelihood that this will be produced. And this is the most energetic reaction with the most energetic isotope of calcium. And it's producing 11.47 mega electron volts. So, there's a potential that if we start with tritium, water, and we have it burning onto calcium, that we can produce a lot of helium and potassium-39. So, and what you're doing is you're capturing the radioactive isotope and producing stable isotopes. Okay? And this should not take a lot of time to do, right? It should not. You get your oxyhydrogen gas. Sorry, you get your sample of Fukushima water. You electrolyze it and you burn it onto calcium oxide. Okay. If we take oxygen and tritium, so if we just look for oxygen-16 and tritium, where's oxygen-16? Oxygen-16. I've got oxygen-16 here. Oh, okay. So the first reaction of oxygen-16 with tritium is helium-4 and nitrogen-15. So okay. So that's stable as well. So. Is it stable as well? Yeah, it's stable as well. He says, if you want to find out if something's stable, go to show element data here on the thing, and we go down to nitrogen. I don't want to get things wrong. And so nitrogen 15 is rare. It's rare, but there we go. Nitrogen 15. What else do we have? I also did a reaction earlier today because of work of Mondaini. He's an Italian researcher, and he did electrolysis in water. And as I'm saying, electrolysis will be creating some HHO. And in fact, that's what he found, an increase in OH in his water. If I need to go back to the beginning here. I did HDTO and aluminium, and if we open that, he observed what he thought was silicon, right? And if you take any isotope of hydrogen and you fuse it with the one isotope of aluminium, you get all of the isotopes of silicon. So this is not surprising. I think I've actually got his thing up there somewhere. Let me see if I can find Mondeini. Give me a sec. Not there. Oh yeah, okay, here we go. So this is Mondeini, cold fusion reactions by Renzo Mondeini, and I'm just going to play it without the audio here. And essentially what he's saying here is, when I used aluminium in water, I found it very interesting because I ended up with this stuff which looked like glass, silicon dioxide. And so where on earth is all the silicon coming from? Where, oh where, oh where? There we go. Now, you could argue potentially that this is aluminium oxide, but it's glassy, which is interesting in its own right. But again, this is a relatively easy experiment to do, so you know, then you can do the analysis. So there we go. I think it's worth having a look at his work, and I think I shared the link in the post before you got started, and this is our chop shop. Okay, so in summary, I think that we can conclusively say, certainly in my view, that oxyhydrogen gases, some may be better than others, are able to produce coherent matter. I believe that that's because they first maze, and I believe that's because of hydroxyl groups, OH, and the hydroxy radical, and that leads to coherence of whatever else is there in the ways that were characterized by, and I'm going to get his name wrong now. What is his name? This is an important name to get right. Characterized by Mr. Low, Shui Yin Low, in in fact, his paper was in, I think, 1983 or 4. Okay. And this is a simple test that can be done. And the fact that we've observed the fact that you need to energize it to a certain level before it will interact with the material. So it doesn't just happen instantaneously. And this is exactly what was claimed and observed by Yul Brown. The method that I think the request for proposal is arguing to use, or is based on, is this kind of electrolysis and concentration technology, but it doesn't actually deal with the tritium. You're still going to put it out to storage and to look after it until it's decayed over several generations. Okay. Of course, you could then use it for something else, but I've given the example of calcium carbonate here as something that is. What I've tried to do is to choose things that are known to have worked in many, many different examples. Choose a technology process which has been proven by Ken Shoulders, by Anatoly Klimov, by Slobodan Stankovic's observations, by Low's observations, by Matsumoto's observations. And all of these HHO observations are ones where we've analysed the before and afters on different metals, and observed extremely strange behaviour, like it is actually acting like a laser, but in this case, I believe it's a baser. And so there are published papers, published patents, and observations that we can do every single day of the week over and over again, and you're going to get the same result every time, nearly instantaneously. So here's the cut line and the effects of the material, which we've discussed at length, transmutations, the observations of the gases in a Mars gas, and the fact that whilst the OH is low and the H2O is in between the H2O and the OH and the H, the H, it's not more than about whatever it is. It's not a lot of percent compared to the hydrogen and the oxygen, but it would appear that when you observe the gas flame by Slobodan Stankovic's work, that the only line you see is OH, and I think that's because these things are being excited, they are splitting up, and you are creating OH as a pathway to creating H2O, but it then mazes. These are other things that can maze, and we've got AH in here and H2O. Of course, if he's going through that graphite crucible, then you're going to get some carbon in there, so you get some other things here which can possibly maze as well, synthesized at the time he's going through there. And he's also doing it in air, so you can get some other things going on. So operating this in air and with carbon in play can give a range of other outcomes. Obviously, if you're using calcium carbonate rather than starting with a calcium oxide, you're going to have the carbon in there as well. So there may be these other options. So this was his observation. I think I did the best explanation for how I think that this is coming about, and I hope that guides him. And I believe that this stimulated this 1980s work by the All-Russian Joint Plasma Physics Research Institute to publish their plasmatron work. But in this case, there's no microwave generator and there's no spark generator. And actually, if you look at the patent, I think it says that you can create anyway, you can go and have a look at the patent later. There's some salient points in there, but I can't quite remember what they are. And we observe the same thing. The difference between, well, this plasmatron here is creating in a similar way to we're creating in the Vega reactors, because we're building up the coherent matter and then it's exploding because it becomes destabilized and you get the ejections of various types that we discussed. And then I talked about the work of David Yerth and how that proved to deal with nuclear waste, and the fact that they were creating the coherent matter structures, the exotic vacuum objects. They were accelerating them, which is something that we can probably do as well if we are generating them something like this. And then into materials, and they were talking about fusion and radioactive remediation, exactly what Lowe was talking about as well. John Hutchison tried to tell me here, but he got the name wrong. On the 6th of November 2018. He tried again 2 years ago, just over 2 years ago, by sending me this image. And that's exactly the image he sent me, all bar some bars from his iPad. And then he sent it to me again a year ago today now. It's a year ago today as I sit here. He sent me this, and it wasn't until yesterday that I realized the significance of what he was trying to say, whether it was intentional or not. And I'm saying, as supporting evidence, we can run the experiment. And the reason I wanted to run this experiment was for this reason, to prove that isotopes, or to see if isotopes that have a longer half-life than tritium can be dealt with by coherent matter in ball lightning type fashion, because I believe that we've showed enough evidence that the NOVA reactors produce ball lightning like phenomena, and that they can transmute matter. And if so, then if we deal with this, I think we can confidently say we can deal with this. So that is what I have for you today. And the fact that I'm proposing as an initial look at, and there's many things you can try with the reaction calculator, but as an initial proposition, you can go to Vietnam and get extremely large chunks of limestone, which is very, very pure, and ship those over to Japan. And you just need a basic electrolyzer, and you blast this gas onto large blocks of calcium carbonate, and that's it. That's the most basic side of it. So okay. Yes, you definitely don't want hexavalent chromium. Uh, okay, so it's okay. Thank you, Dan. That's kind of you. Yeah, you definitely don't want any chrome in your electrolyzer. That's a cancer carcinogen like no other. Bob Kenter, Bob G, the master will appear when the student is ready. Yeah, I think so. So the thing about the electrolyzer is it has to last a long time, and I had this discussion with Slobodan earlier today. And I think we worked out from figures that were given to me by Show that the electrolyzer Amaza runs at about 58% efficiency. So if you need around about 8 megawatts, you're going to need, say, 15 megawatts to run it. Now, that's still quite doable. And you can scale this. This what I'm proposing is incredibly scalable, and the test is very trivial. So we are essentially creating water gas, whatever that is. Amasa gas seems to be the gold standard. The great thing about Amasa gas is that the plates are large. They are physically easy to replace. And there's relatively large gaps. So if you look at the videos, they're kind of like quite n numbers of n times of. Sorry, there was a disconnection there. I don't know what you missed, but n times of electrolyzers, and so if it's going to be a similar kind of efficiency to Amasa gas, or let's say it's 70% efficiency. If you've got 10, that you need 10 times the amount of electricity if you're doing it over and over and over again. I'm proposing you just get the tritium into either ditritium, TD, TH, the various versions you can get, and then you burn that like in your Brown's gas type, Amasa gas type flame onto a target. And the target should be something that would really want to react with it. Now, aluminium, I believe, is very good at reacting with it. But aluminium could end up as a big molten blob or mess and get very messy. And if silicon's produced, then, you know, it might make the matrix very difficult to work with. Calcium seems to glow brightly. Now, if that brightness is part of the mazing process, it could just be that you get helium and hydrogen out of it. In fact, have I done the reaction? There's some other reactions that come out of this which are very, very favourable, where you end up losing the two extra neutrons to calcium, say, and you just end up producing protium. So you're kind of like just capturing those neutrons into another isotope of calcium. And so I think that might have been iron. But anyway, it doesn't matter. The point is that what Lowe is saying is that using the concept, if this is producing coherent matter and everything's pointing to the fact that it is, and we know it can transmute material we use and impinge upon it, then choosing the matter is a case of going through different pieces of material. And you could have like carbon rods, your sample rod, which just moves underneath the flame as it goes, you know, and does its process. But I'm kind of envisaging not dirty as in the result, but like simple technology. My ideal one is electrolyze it, gather the excess energy and use that to generate at least part of the electrical energy needed to do the electrolysis. And ideally, your tritium would do what matter seems to do with these systems, and it would reorganize into stable elements. And your target would basically be chalk, and that's it. And what you would get out of that is water and probably potassium in water and other stuff, because there will be cascade reactions. You're going to get iron, you always do. Yes, Bob, that's right. It is you when you're ready to hear. Yeah, WP for truth. I would like to see it produce lots of excess energy. The reality is that if you look at the reaction tables, that there's so much room for creating vast amounts of energy. I mean, it's comical. So you know, uh, tritium and calcium 40 goes to helium and potassium 39 with 11.477 mega electron volts per interaction. That's a phenomenal amount of energy. That's a phenomenal amount of energy. Yeah, I've seen the Salvatore Paya paint, and it looks a little bit complicated. Listen, now we know and can repeat every day of the week that you can do transmutation with at least I know from a Marsa gas every day of the week. I would like to have not had this cold going about and been able to go and test the Brown's gas generator last year rather, and have verified that Brown's gas does the same thing. So what? You know, it gave me time to think on other things, and so whatever it has happened has happened. Um, I'm pretty confident it will do the same thing, and part of the reasons is what Matsumoto observed ultimately was that everything whatever happens, it tends to produce a lot of carbon. That's what I observed, and that is what uh, um, Yul Brown was claiming in public in 1988, and so it's very likely that all of these systems will do exactly the same thing. Now, that Alexander Parkhomov suggested ultrasonics. Well, ultrasonics we know, and cavitation, we know it can do transmutation. But and in fact, Amasa has already used his vibrator and shown that it can take tritium water from Fukushima, and in 1 month it can lower its radioactivity level to effectively 2 half-lives. So it's 0.25 of the activity it was to begin with. But that takes a month, and there's a lot of vibration for a month. Okay, so it's not going to be able to deal with, firstly, it won't deal with the amount of material that needs to be dealt with. And secondly, it's not going to be able to, how should we put this? There was no scientific explanation for it. Now we have an understanding why it's doing it. It's because it's cavitation. We know that now, and we know that is in other journal articles. So, but it's not fast enough. That's still the problem. We know that Brown's gas, HHO, and what we use with the Marsa gas, that's very quick, and so that's where I would you know, put the flag. Yeah, there's a competing patent that is still actually valid that took, I think, Amaza's technology and used piezo. So piezo can do sorry, I forgot my point that I was trying to make there. If you overcavitate, you will produce heavy elements, and then you will create super heavy elements, which will fission, and you won't be getting rid of the tritium. You'll be creating transuranics and all of the nonsense that you normally have out of fission reactors. This is also what Leclerc did. So you could think that the best technology would be to use a hydrosonic pump, a heat generator, but you will end up with so much hot material and producing so much strange radiation, it would just be really seriously dangerous. Now, I have thought of a strange radiation generator like that and pushing that into the reactor and using that to decay other material by working at a proxy. So you end up with one hot thing and everything around it is being decayed, all the beta isotopes. So that is an approach maybe that can be taken there, but you know that's a lot of testing that needs to be done before you get there. The point about and we know this. Sorry, we know from the Echo fuel generator that it synthesized. It would seem a lot of lead, and a lot of people have observed lead. And if you keep pumping beyond the lead, you end up with these heavy elements. But we didn't observe super heavy elements in the Echo fuel, but lead seemed to be generated. The problem with the other thing that he suggested, the hydrosonic, I think it's hydrowave technology. This is another Russian technology that is claimed to work, but there's no evidence for it. The thing about Brown's gas is I've seen it work. Brown's gas claimed it did X, Y, and Z, and that's exactly what I observed. I would like to test the actual Brown's gas generator, but seeing as Slobodan Stankovic observed very similar formations of things that produce the same things, and that those things are in line with what Matsumoto observed and the claims of Yul Brown. This is tested. Moreover, it's really, really, really easy to verify. It's really easy to verify. So by having experts like Matsumoto, by having experts like Amaza and like Slobodan Stankovic, we come together and join our forces. We have current experts in the field that I believe is well tested and has already shown remediation of nuclear material. It's just we can't just go out and buy a good chunk of radioactive material and test it, and that is a real problem. So the most important thing we have to solve is how do we get access to the tritium water. Yeah, you get a 2-for-1 with the Amaza vibrator plates because you get some remediation and cavitation and coherence on the actual vibration, but he alternately polarizes each plus negative on the potential to electrolyze the water. So you get a 2-for-1, but I think the real money shot will be the optimizing the production of the coherent matter. And I believe the fact that limelight is so intense, I kind of envisaged what you have in the plasma jet coming out of an Amaza gas jet, as I described it. It's hitting the 10 yen coin. There's a reflection of the beam back to the back of the plasma channel, and that creates a plasma mirror at the back where you get the change in state, and that you can get your intensification of the energy. In the case of Yul Brown, as I said earlier, he's putting it on the material and he's loading it, And if you look at Bogdanovich et al.'s work, when they are doing the plasma flow discharges, they get these structures that are active for 2 days. Now, if you imagine you're loading it on trillions of these things on top of each other, on top of each other, on top of each other, and we've shown, or it's been shown in Bogdanovich's work, which is essentially, when you squirt water through a jet, you get a charge differential. And in fact, that's exactly one of the patents of Low. One of the patents of Low. You can go and have a look at it. And then if you discharge through that, you're effectively creating, in my view, essentially oxyhydrogen gas and everything you need to create EVOs and coherent matter. And so that can build up into the structures that they see, which are exactly what we've observed on various different examples of this family of technologies. And they can build up, if they can last for 2 days, and you're piling them on top of each other, and they like to join together, as we've seen in the Vega experiments. You can see 2 here, and you get more energy, and they join together. Or you have balls of fire, or Sapphire I like to call them tufts, all over a sphere, and then you get more energy, and they join into one double layer, and then another layer, and another layer. These things self-organize, and that is what I believe Yul Brown sees when he's putting the gas onto the aluminium and the iron. I've explained the roles of the aluminium and the iron and the radioactive material. It builds up one coherent matter thing, and when it gets to a certain level of coherence, nothing can stop it. And in an instant, and it is really in an instant, and you can go and look at the Vega experiments that I've shared, like the tungsten chop shop, and you can see that it is an instantaneous moment at when all of the action occurs, and everything happens at once. Yeah, a 2D array of needles, or even a 3D array of needles. I imagine something like, you could, if you wanted to capture the energy, I mean, it could be just a huge 2D arrange of needles onto some raw mined chalk, like limestone. You can get these wonderful quarries in Vietnam where they get this beautiful quality, highly pure limestone. And you can either treat the top surface to start with and make it lime, and then you just have thousands and thousands of nozzles, and they're just burning onto the lime, and away you go, job done. And I would hope that you produce a lot of potassium, and you would produce a lot of normal water, which comes off as steam, and then you condense it. And helium. I think, how do you shield yourself from radioactive tritium gas? Well, you know the electrolyzers. I mean, people can build electrolyzers that work every day of the week. Okay, right? And you can build a jet, and you can have that electrically ignited. Okay, so you don't need to get close to that. And the whole thing can be in a sealed chamber. And if you're only producing a few litres of tritium oxide, TTO, or you're only producing a few litres of T2 or TDO, or T2 or TD or TH in your electrolysis, then if some of that vents into the wider atmosphere at a distance, and given the whole scheme of things, I think in terms of testing, one has to accept that is a real possibility. I'm sure that there is an amount venting anyway from the reactor that would far surpass any test we could possibly do. And then once you've got the technique sorted, and you can see that the transmutation occurs, and that you are getting water out, let's say, and helium and potassium formed, let's say, in this instance, as a example embodiment, then it's just scaling, and anyone and their dog can make this technology. It's really, really simple. And so I've reached out to a person at Mitsubishi, I haven't had a response yet, but it would be great if they could say, yeah, look, you know, if you've got a working solution, we'd be happy to make it. And they've got all the industrial might in order to just go ahead and just knock it out. Yeah, it would be great to get a phantom camera on those. It's one of my things that, you know, doing higher speed photography of the kind of things that occur. For instance, like the one that I showed with the indium, the hair thin indium that's supposed to melt at 156.6 degrees centigrade, and it just turns into a jelly sheet and it's flapping around in the high speed jet like that, and it's a metal that should be molten a long time ago if it was really hot. Okay, so maybe we will have just a straight Zoom chat on Sunday. If you can install Zoom on your computer, and at some point I will put out an invite, and maybe WP for Truth can share his things on Sunday. If you have any ideas, if you want to work the Parkhomov reaction tables at nanosoft.co.nz and come up with other suggestions for the target material, we know we're going to be producing TT, okay, and variations with oxygen in play. So you can look at maybe the reactions that could come out of it, and propose other options. I've looked at quite a few, but I like the idea of calcium because the raw material is just a block of stuff that you cut out of a mountain, and what could be simpler than that? Well, I mean, when on a massive scale, there Yul Brown worked in China, and I think they gave him, I don't know, 35,000 employees or something, because the Americans wouldn't work with him and the Australians wouldn't work with him. And they actually developed HHO cutting tools, which can cut through incredibly thick pieces of pig iron, like incredibly thick. And when you see what it can do, you kind of think something special's going on, and I think this is what it is. It's coherent matter, and it creates a coherent matter beam in a direction. Yeah, I'm saying can present on Sunday. Blues Doctor, I will post the presentation with all of the links in it as soon as I get back home. In fact, so you should have it on the remoteview.icu. On remoteview.icu, Blues Doctor, the last presentation. So you'll be able to go and see the patent. But I think, Blues Doctor, this is done. Unless they want the tritium and they want to look after it for several hundred years, or they want to dump it into the ocean, I think hydrowave technology might work. Ultrasonics, I think if you pushed it too hard, you'll end up getting more problems than you started with. Not necessarily if you're flowing it through, so maybe hydrowave technology will work, but I can't say whether they'll work. It's just claims. What I can say is what I know about HHO, Brown's gas, oxyhydrogen gas, Amasa gas. We have seen it create plasmoids that last after the experiment. That is what was observed by the Bogdanovich team. This implies to me, along with the transmutation that we've verified, that this will work every day of the week, and Yul Brown was right, and his demonstration should have been adhered to in 1992. Maybe he was an abrasive character. I don't know. I think he seemed to be quite affable. Maybe the people weren't ready to know that something so amazing could happen with such a simple technology. I don't know, but it does, and people need to get used to that. Yeah, so it's an interesting thing, and it's very fascinating to have gone through that realization live on camera on Sunday, and gone on Wednesday when I was on the train. I was going, God, what did John send me? I know he sent me something. I found this paper, the patent application from Lowe, and it basically explained exactly what we have been doing, creating a coherent matter, which I assume was doing the job, impinging it upon another material to effect a transmutation. Fusion was what he was interested in his paper. And then just to find that let's find out what the Baser was that John sent me, but then that image, it says this Lowe name. It's like, oh! Yeah, I mean, when you think of the extremely complicated, uh, if you have the extremely complicated thing that the Lockheed Martin are doing to create their coherent matter, it's almost laughable. Matsumoto was suggesting using something to create bunched electrons, which would be I imagine a free electron laser, like was being used by Solin in his coherent matter nuclear reactor patent from 1992. So he's using coherent matter, but and a LINAC. So he's using a free electron laser and a LINAC to create his itonic clusters, and even the Lowe paper is using a complicated piece of equipment when really it's an electrolyzer and set light to it and you're off to the races. It's just crazy. You know what? The question about venting H T T TTO, sorry, TT2, TD2, sorry, TD and TH, you could have a problem with that. The interesting thing is that every the 3 atoms of every 1,000 fission atoms, or sorry, every 3 out of every 1,000 fission events in a normal nuclear reactor produces 85 krypton. And 85 krypton gets released into the atmosphere. And it's actually one way that they find out how people are trying to get plutonium, because it creates so much higher ions in the atmosphere that you get increased lightning around it. But also, it's very heavy gas, so it stays down where animals live. Tritium will, T2 will just go out into the upper atmosphere, So we'll talk about 85 krypton. I've talked about it in the past, but I'll talk about it again because I'm going to look at. Maybe I'll do this on Sunday. I don't know, but on reinventing or revisiting the Tesla carbon button light bulb, and I was considering it for that. But it's one of these beta isotopes, which is, in fact, Ivan Filimonenko, who was the first person to do a palladium deuterium boiling water reactor in the 1950s, I think in 1957, but it was under secrecy, so Pons and Fleischmann get the credit. He complained so much about dumping krypton 85 into the atmosphere that they locked him up in Siberia, I think it was, like in one of the gulags. They didn't want his message getting out, the fact that all the plutonium production from the RBMK reactors was producing all of this krypton 85 that was just being dumped into the atmosphere. So that's much nastier. And every single time you charge your iPhone, unless you're doing it on your own, like exercise bike or something like that to charge it, you're probably contributing to some production of krypton 85, particularly if you live in France or the US or South Korea or China. You're going to be assisting the production of 85 krypton into the atmosphere. Tybor, a summary of the work is the project was set up to test the claims of others in the low energy nuclear reaction field. Over the years, we've done several experiments, and one of the most valuable ones was our first one, which was with Francesco Celani, and that work enabled the European Union to consider supporting this research with real money, and they've now assigned about 11 million euros to two groups, but many universities are now researching, in part because of what we did, because Francesco Celani was brave enough to share his technology for review by us, and we were able to verify his claims. And then we verified other people's claims, and some of the claims have not turned out to be anything serious or nonsense. But over the time, the understanding has grown, and we're at a stage now where you can see that all of these family of behaviors working from absolute zero into millions of degrees only happen because, in my view, of coherent matter phenomena, and these things create charge clusters, which then can lose their mass and inertia because they start acting like one electron. So that it's kind of like a bit weird, but the deeper you dive into it, you realize the more historical supporting evidence there is, going back even more than 100 years. And so I think people just don't care enough to do the hard work, to look at the work that's already been done. And every other month you see someone else reinventing something that's already been done. Even some big proponents in the field claim they've made a new invention, and they just haven't. I mean, you know, for instance, there are people that are using carbon to stop their reactors from falling apart. This is one of Ken Shoulder's exotic vacuum objects patents, and in here it specifically says, in order to stop your reactor from being destroyed by exotic vacuum objects, you need to use a light atomic nuclei, and it suggests carbon. There you go, and it's like in there, and it's like, yes, we're protecting our amazing energy generator by putting a layer of carbon on it, and well done. Perhaps you could have read the literature. People can't be bothered. They'd rather spend 10-15 years and the $10 million reinventing the wheel than going to see if someone's already done it. I can honestly say that I didn't come up with the concept of paying attention to what's already been done. It wasn't. I started volunteering for this in 2012, and it wasn't until I visited Francesco Piantelli in 2015, in January 2015, only made possible by donations from the crowd, and he was infuriatingly impassionate when he says, I don't understand why anyone thinks they're inventing something new. Most of this stuff is in the literature for over 100 years. And he was pacing around this gargantuan library he has in his house and pulling books off the shelf and look, la 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 la, it's here, la 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 la, it's here. And, you know, that's the truth of the matter. But also there's a lot of dross as well. And so it's finding out the pearls out of, you know, all of the not so very good oysters. I don't know whether that's even a phrase, but I think you know what I mean. Dan, that sounds like quite a. She's talking about Tesla using carbon electrodes. Yeah. Well, there's several things about Chernobyl. You're definitely not getting. Don't HBO's Chernobyl miniseries is one of the best pieces of television ever, but it is just perpetuating nonsense. But it's great television. I loved it, but it's nonsense. All right, I'm going to call it a night. So thank you very much for your time in this middle of the week session. It's been a real pleasure. I think we have a real path forward here. Anyone that believes that they can assess any better ways of doing what I've suggested, go and read the patent that Lowe put out. Put it in context with the other coherent matter presentations, particularly the coherent matter traveling wave beams and stuff that I've put out, and the patents and papers surrounding that. This is what we saw in Dave's Vega experiment can only be explained by coherent matter traveling wave beams, and those, along with the ones observed in Henk's experiments, explain all of the strange radiation tracks. And the fact that coherent matter in the form of sort of mazing matter and this kind of thing produces these beams of magnetic energy, that explains the extreme interactions that we saw. And it just goes to show how intense those beams are. Okay, David. Well, I recommend you go see it and go and have a look at the patent as described. But basically, John Hutchison spent 2.5 years trying to hint that I should be looking at basers. Whether that was deliberate or not, I only clocked it on Sunday, and I found this patent. The patent explained exactly what we're doing and the whole history of where I'm gone with Amasa gas and HHO and so on, and the observables are showing the claimed range of electronuclear reactions that Matsumoto had observed and written about, and it's just amazing. It is so simple. The Egyptians could have easily done this. They could have easily done this. I mean, the Baghdad battery's been around, what, 5,000 years or something? They only need electricity, water, and some way to ignite it and put it through a tube. They could have used, I don't know, a porcupine quill if they have those there. I don't know whether they do, but they could have used something like that. Had the little jet coming out, and they could have done all kinds of stuff with it. Okay, so thank you very much. I'm going to leave you. Good night, and I will see you on Sunday, probably for just a Zoom chat and for WP for Truth to show off his gear. So thank you very much. Sayonara, dobro noc. I'll see you. I'm too tired. Good night.